So now in McDonald's, the notation is a little bit different than what I'm using, but I want to make the connection. In McDonald's notation on page 370, he has the formula that C, the price of the security, is equal to, you'll notice the CH and the CL. And then you have QH and QL. QH and QL are, in fact, the prices of $1 investments that are only paid in the high state, that's QH, or the low state, that's QL. And if you compare his formula to my formula, you will see that, consistent with his footnote 6, that QH is equal to P times UH. And here's UH. He mentions in the footnote that UH, it's a utility, it's a discounted utility. And he makes the point that it's the present value of a utility that's average. So you see that what I'm doing here is taking the utility value at CH and dividing by CH, in a sense creating a utility value per dollar of CH. And that's the value of... So this, while the notation that he uses may look a little bit unusual, it's entirely consistent with the more traditional approach to utility theory. However, in his notation, once you calculate QH and QL as these expected values, then you can price with them very easily. In other words, here, if I have an asset that gives me CH and CL, two different values in the two states, I use this formula. If CH is equal to CL, equal to $1, like a T-bill, then the price is just the sum of QH and QL. So once you get through the notation, it's easy to work with either approach. So now with this, we want to calculate the risky assets return. And what we're going to now observe is that we can also price options with the risky asset returns. But it's much harder, and it involves knowing something that we would not know. And that'll be clear in a moment. So first of all, what is the risky assets return? Well, we see that the risky asset on the top, this is the expected value of C at time L, at time the future time, and this is the price. So if I take a look at the expected value of the payoff divided by the price, that's what these are, right? And that would then be 1 plus the expected return. So alpha is the expected return obtained by taking the expected payoff divided by the price. So now, I mentioned in my introduction to this section that a risk-averse investor can act as if they're risk-neutral if they change probabilities, and that's what we're going to do next. This risk-averse investor originally had a probability of P for an upstate, and that's how this investor did their pricing. So now we're going to define a new probability, P star. And what we're going to show is that this investor will get the same price with P star, and assuming that they're risk neutral. And just the math, if I take P star, if I look at the original price of the security, which is this, and with that value of P star, it's equal to this. Notice how we've gone from, on the left, an expected utility with P, to on the right, the expected payoff at P star. That's what's happening as I go from left to right. The left equation comes from an expected utility, which is traditional pricing for a risk-averse investor using P, the correct probability. And by changing the probability from P to P star, we can go from expected utility to expected present value of the payoff itself. We can eliminate, in a sense, the utility function and the discounting all go into the P star. Well, the discounting does not. The discounting stays outside. So a risk-averse investor can act as if they're risk-neutral if they simply change their probabilities. And this is the reason that risk-neutral pricing works. Even though the market is indeed risk-averse, the price of the option, assuming they were risk-neutral, is correct because what we've done is change the probabilities of events from the P model, the real world, into the P-star model, which is the risk-neutral world. And in the same way as here, we can price, and in the example of the appendix, we can price risky and risk-free investments with P or P-star, using utilities or not using utilities.